Great, so let's get started. So my name is Billinghurst. I'm the session chair for the session on collaboration, session 23, and we've got 4 really exciting speakers today. The first one is an old PhD student of mine, Allison Jing. She's now working at RMIT, and she's going to be talking about some of her new work on emotion, and particularly the title is Superpowering Emotion Through Multimodal Cues in collaborative VR. So I'll turn the time over to you, Allison. How do you go?
Thank you, Mark. Hello, everyone. Good afternoon. My name is Allison Jing. I'm from RMIT University from Melbourne, Australia. Also, Empathic Computing Lab from South Australia. I work with Mark very closely. So today I'll be presenting our paper titled Superpowering Emotion Through Multimodal Cues in Collaborative VR. If I can just move it up a little bit. I guess I can't. Oh. So understanding emotions can be challenging as we mostly rely on facial and verbal expressions to feel others in the physical world. Virtual environment enables humans to express emotion beyond their normal abilities as between collaborators by augmenting the subtle and easily missed feelings in real life into supernatural virtual phenomena in VR. So this research, we will explore how multimodal cues can be used to create better spatial-temporal superpower representations to understand emotion in collaborative VR. So first, we would be presenting a system, see that well. A system augmenting users' virtual surrounding space on the change of the emotion state, which is considered as superpower by us. And second, we will propose a spatial temporal evaluation metrics into existing subjective and objective measures for the more comprehensive empathic VR experience. And lastly, we will conduct a user study to understand how multimodal sensory representations affect emotion in VR collaboration. There are 3 factors that motivates us to conduct this user study, this research, which are multimodal sensory stimulation, emotion representation in VR, and sharing and measuring empathy in VR collaboration. That leads to our first research question, which is modality-driven, how different modalities stimulate emotion between VR collaboration. And our second research question is about representation. How do subjectifying and objectifying affects the emotion representation in VR? By defining subjectifying and objectifying emotion, we basically consider facial and verbal expression provides a direct intention to indicate human emotion when constructing a one-to-one human form representation in VR. But for those non-human or supernatural representations, such as augmentation of the immediate environment around the collaborator, is basically defined as objectifying emotion. So basically, what you want to express to people is subjective. What you receive from the overall environment is subjective. And the last research question is about usability and evaluation, which is how to incorporate spatial temporal aspects into existing metrics to understand empathy in VR. To address the research gaps and answer the asked 3 questions, we designed an emotion sharing system prototype that provides 3 types of sensory stimulation, including textual, which is reading text content, auditory, which is listening to the content, and visual audio-visual, which is listening and viewing the content. We also have 2 representation factors, including a natural human form, avatar, can be turned on or off, and a superpowering environment, which can also be turned on or off, and 6 discrete emotion visualizations, including anger, disgust, fear, happiness, sad, and surprise, the facial and verbal expressions on a human form avatar, as well as color change and particle effects in the environment as a superpower. For the user study, we have 28 participants with an average of 28.7 years old, recruited from the general public. 32% were female, 39% reported being native English speakers, as our system was actually conducted and studies were conducted in English. 79% consider themselves as empathic, refer to compassion or understanding of other people's feeling. And 46% are VR experts. We also have 15 text corpus marked as 5 positives, 5 neutral, and 5 negatives. The references were selected and tested to be within 15 seconds. We also have 2 factors that are examined as avatar on and off, as introduced earlier, and also superpower on and off, forming 4 conditions: audio only, avatar only, superpower only, and full immersion. A pre-study textual references was used. The goal is to understand which factor may elicit more emotion between virtual avatar collaborators. The system was built using MetaQuest Pro to capture facial and eye gaze data and Shimmer 3 sensor GSR Plus kit to capture EDA data. For the task, we have a pre-study phase. The textual stimuli were randomized and appeared in the center of the virtual environment, and 5 seconds resting stage, which was provided before proceeding to the main 15 seconds viewing time, followed by prompting to answer subjective readings after each trial. The VR environment features an empty gray room representing a neutral state to ensure participants receive minimal distractions. We have the main study as a second phase, comprises of 4 conditions based on the level of auditory and visual stimuli and factors of avatar and superpower. An actor was employed to record 15 trials of express emotion through avatar, which is the subjectifying emotion, as we mentioned earlier, and superpower, which is objectifying emotion, as visualizing the environment around the superpower, as designed previously. The procedure stays the same in the pre-study phase. Physiological data such as GSR or heart rate were recorded in the pre-trial sessions as a resting stage baseline, and during the trial as the actual EDA data collection. So 5 seconds rest, 15 seconds study, and then post-study questionnaire. We also propose comprehensive evaluation metrics that incorporates the spatial temporal elements of the virtual environment called RICAS, realism, immersion, connection, spatiality, into commonly used self-assessment mannequin questionnaires, SAM, and physiological and behavior measures such as heart rate, GSR, gaze behaviors. We also collected preferences and qualitative data. For the subjective results, user ratings suggested a audio-visual modality with the collaborators' avatar and superpower environment posed more emotional arousal, especially positive emotion. The avatar with the superpower provides the best recursive experience, where understanding, connecting, and immersion in the collaborator's emotion is spatially well represented in VR. According to qualitative feedback, subjectifying emotion via avatar creates more straightforward understanding of the emotion, leading to easier provoking and investing in each other's feelings. Contrary to objectifying emotion states via superpower alone, it lacks standardized visual representation, which sometimes causes confusion due to different interpretations from different people. The combination of avatar and superpower provides the best experience in emotion sharing and understanding in collaborative VR. For objective results, according to physiological measurement, heart rate is higher with auditory than textual stimulation, but there's no significant differences among other measures, potentially suggesting that the auditory might relate more closely to heart rate in VR emotion representation. On the contrary, GSR showed the user were more aroused by superpowers, which higher tonic and physic values indicate a higher sensitivity and reactivity towards environment changes and exposure. This was also confirmed by the increase of blink frequency when superpower was enabled, suggested that users may be engaged in higher cognitive visual demands. And the blink duration also become longer when no audio-visual simulation was presented, suggesting potential fatigue or relaxation, hence less cognitive processing and engagement. In behavior measures, users divide their attention when more visual representation are available. When superpower is enabled with avatar together, users split attention to the in-situ surroundings instead of focusing only on the avatar's eyes or face to pick up emotion signals. Potentially, emotion understanding was not necessarily obtained only from the continuous direct eye contact and facial expressions, but it can be combined with the augmented emotion states as a background environment as confirmed by the user preferences. there are four elements we want to discuss in the discussion session. Avatar alone is straightforward, but requires continuing attention, while superpower alone is more aroused, but lacks standardized representations. Combining subjectifying and objectified emotion together through a human-formed natural avatar and superpowering environment makes it easier for users to invest and recognize emotion better, amplifying positive emotion and encouraging more focus on each other's emotion. VR experience and preferences. For VR experiences preferences, VR experts least prefer audio only, and novice users actually least prefer superpower, suggesting experienced VR users are more accepted to using arbitrary fabricated 3D visual representation to convey complex emotions, while novice users are more reluctant due to their limited exposure. 26% of the empathic participants like single modality, which is audio, but not empathic participants who are consider themselves not empathic, all prefer multimodality. So we suspect more empathic people are actually sensitive enough to rely on a single modality to understand emotion, while not so empathic people may need more modalities to help them understand each other's feeling better. For non-English native speakers, reported having no difficulty understanding content to exert emotion, suggesting no bias between English or non-English users among modalities. 73% of the non-English users prefer multimodal full immersion, whereas only 35% of English speakers do that. This potentially indicates that the subjectifying and objectifying emotion representations as a whole package assists users whose primary language differs from the communicated language, with a higher level of usability towards collaborating with empathy. To conclude, this research explored how emotion can be represented in collaborative VR through two spatial-temporal factors, natural avatar and superpower environment, using three sensory modalities: textual, auditory, and visual. A human-formed avatar is used to visualize a continuous natural facial and verbal expressions, and the superpower is augmented to emphasize emotion state over the period of time. We provide methods for selecting reference database as stimuli, propose evaluation metrics to accompany physiological, which is basically GSR and heart rate, and behavior measures such as gaze, as well as providing general design insights for users with diverse backgrounds using multimodal representation in empathic VR system. In the future, we plan to expand the study into real-time multi-user domain-specific scenarios where emotion consensus or shared feelings are represented via explicit facial or verbal expressions, as well as implicit physiological cues in various modality formats. So that concludes everything we have in this research. Thank you very much. If you have further questions, because of time limitation, please feel free to scan my LinkedIn code and then just shoot me a message. Thank you so much.
Great, thank you, Allison. So does anybody have any questions for Allison? I think there's a microphone. There isn't a microphone, but you can take it around the room. Any questions in the room for Allison? I had one question. I think you said something really interesting, which I just made a note here. Mm-hmm. So you said that you felt that people that didn't have so much empathy needed more modalities.
Yeah.
Can you explain more about that and why you think that was the case?
Yeah, so we basically conducted qualitative, not interview, but more like a questionnaire with them as well. So asking them, how you feel about yourself and how you feel about using all the modalities. Surprisingly, we also found out that the people who consider themselves less empathic actually preferred multimodality. We didn't really have follow-ups interviews in terms of how they feel, but we suspect that could be, people who have a hard time really understanding each other might need multiple different type of representation to actually help them understand each other. So potentially for those people who have trouble expressing themselves or trouble understanding others, those type of systems would be really helpful for them to build a healthy relationship in the future.
So, for example, maybe they're using haptic or tactile modality of input as well?
Yes, that's exactly what it is.
Great.
Okay.
Does anybody else have any other questions? Otherwise, Allison will be around during the lunch break. You can catch her, and she's got really helpful to put her LinkedIn profile on there. And I believe, can you check online to see if there's any questions on the Zoom link as well? And I think there's a Discord channel for this paper as well, so if you want to ask questions on Discord, you can do that as well. Anything online, Katja, or is that? Okay, that's great. Great. Well, thanks, Allison again.
Thank you.
Nice job. Thank you so much. And next we're going to have Anca. So come up here and I'll see if we can the cable here. And it's one of the ends, okay, great. Okay, let's see what happens. It's coming. Yep, great. So this is Anca, is it Salagean? Okay, great. And she's from the University of Bath, and she's going to talk about watch out, XR mobile displays improve the experience of co-located VR gaming observers. It's like a really interesting topic, so I'll let you take it away.
Thank you. Hi, everyone. My name is Anca Salagean, and I'm a postdoctoral researcher at the University of Bath. And today I'll be presenting our paper that introducing a very simple and affordable system that improves the experience of collocated VR gaming observers. So before I get into the specifics of our implementation and our user study, I'll briefly talk about the general background of our work, which is collocated VR gaming. Collocated gaming in general is a commonplace experience where two users can either play at the same time, or what is the case of our paper, one of the users, the player, actively engages with the game, whereas another user, the observer, takes a more passive approach and is viewing the gameplay as it's happening in real time, and can socially interact with the player by giving them advice or pointing out elements of the gameplay that the player might have neglected. And VR has been shown time and time again to improve the experience of the players in gaming by creating immersive and emotionally stimulating experiences much better than 2D screen-based games. But at the same time, a VR headset creates a perceptual and cognitive barrier between players and observers, thus hindering the experience of the latter. And this has been found in many papers, and there are now different prototypes built to improve this limitation of VR gaming. Because, as I said, like the status quo right now is for a VR observer to watch the gameplay on a fixed screen with very limited opportunities to engage with it. So, as I said, current prototypes have been built that give observers the possibility to engage with the game and to either have control or agency over certain parameters of the game, such as their viewpoints, and even ways to engage with the player during the gameplay. However, many of these implementations require specific hardware that it can sometimes be expensive or is just not accessible for the typical VR gamer. Also, many of the papers that introduce such systems tend to focus on the experience of the player rather than that of the observer. So it's important to acknowledge now that there are very many types of technology that are very easily available for the typical VR gamer, such as just standard displays, webcams, trackers such as the Vive trackers that are often shipped together with the classic HDMIs, leveraging computer vision and such simple technologies, observers can now get better experiences, which is what we aim to produce in this paper. So we pose the following research question: how can we improve the experience of observers in collocated VR gaming? And in order to address this question, we formulated the following research questions. So research question 1, how does giving observers agency over their viewpoint affect their experience? How can a mobile XR display improve the experience of observers in collocated VR gaming? And finally, how does using the player's live appearance in the observer's XR view affect the observer's experience? We aim to answer these research questions by creating 4 configurations. So 2 of them involved the observer watching the game playing on a stationary screen. So in 1PP, the observer watched the game playing on a stationary screen from a fixed first-person player's perspective. Previous work has shown that this type of perspective is preferred to a fixed third-person perspective of the player, so we did not include that type of configuration, but instead we used 3PC, which was again experienced on a stationary screen, but the observer had a gameplay controllable third-person perspective, so they could, using the gamepad, take different perspectives of the player that the player did not have at this specific point. Then we used two conditions where observers were given an XR-enabled mobile screen, which you can see here on the slide. So you can see that the configuration is very simple. It's just a classic display with a webcam. There's a Vive tracker, which you can't see, which is attached to the back of the display. And essentially, the observer can take this display, move it around, go further in any direction, and take any sort of visual perspective they wanted to, which the player, again, they didn't have that. In GXR, you can see that the player is represented by a generic avatar that we opted for in order to match the game aesthetics and because we wanted to have a standard experience for all of our players and observer dyads. And in PXR, you can see that the player is represented by live video footage. So we were interested to see if this addition adds anything to the observer's experience. So we had a within participants design, so all of our participants took part in all of these conditions, and we tested the 4 configurations on 24 dyads of friends, 33 males and 15 females, and we opted for friends because we wanted to have an ecologically valid implementation, and we really wanted to see like natural interaction between our participants. In terms of the game, we chose Superhot VR because this is one of the most popular off-the-shelf games at the moment. And at the same time, this specific game has in its mechanics a feature that was helpful for us. To be more precise, in this game, when the player is stationary, the action freezes. So what this means is that while the player can be static, the observer can move around and inspect the area and essentially identify the enemies, so then when the player moves, they're ready to attack their opponents. So again, we chose this because we wanted to have ecological validity and also because we wanted to encourage the interaction between players and observers and give the observers opportunities to actually be as involved as possible in the gameplay. But at the same time, this is one of the most popular first-person perspective shooters out there, so the findings still would have generalizability to other games that are similar. In terms of our variables of interest, we were interested in the observer quality of experience. So we measured observer's presence, all 3 dimensions of presence, physical, social, and self-presence, and in the intrinsic motivation, so especially the interest and enjoyment, perceived competence, and effort and importance subscales. As a manipulation check, we also measure perceived agency, and also, we measured all of these variables, both for observers and for players, as an extra exploratory investigation to see whether the 4 configuration could, in fact, also impact the experience of the players alike. So we formulated the following hypothesis. So hypothesis 1, when using the 3PC, so this is the fixed screen but controllable viewpoint, observers will feel higher presence and intrinsic motivation compared to 1PP, which was the fixed screen with the fixed first-person perspective. When using GXR, observers will feel higher presence and intrinsic motivation compared to 1PP. So GXR was the XR-enabled mobile screen compared to the fixed screen fixed first-person perspective. And finally, when using GXR, observers will feel higher presence and intrinsic motivation compared to 3PC. We were also interested in the comparison between GXR and PXR, so this is the different player representation. But this was an exploratory investigation because it seemed that the literature in this area it had mixed findings, so we didn't want to formulate a directional hypothesis. Instead, we took an exploratory approach. So what did we find? Well, first of all, we found that in terms of perceived agency, 1PP was rated significantly lower than 3PC, GXR, and PXR. So this means that the manipulation check was met. So even providing the control over the viewpoint on the fixed screen led to an increase in agency compared to the fixed viewpoint, which was also lower than GXR and PXR, which you can see on the figure on the slide. Looking at the observer presence findings, we found that both 1PP and 3PC were rated significantly lower for physical and social presence compared to GXR and PXR. And similar trends were found for self-presence. So what this means is that giving people giving observers the XR-enabled mobile screen significantly boosted their presence during the gameplay. And again, you can see the trends in the figures on the slide too for both players and observers. And in terms of the intrinsic motivation variables, 1PP was rated significantly lower for interest and enjoyment, perceived competence, and effort and importance compared to GXR and PXR. So again, providing the XR-enabled screen led to a better experience across the board for the observers. In terms of the GXR and PXR comparison, we did not find any significant results. It seemed that providing the live video footage of the player did not significantly improve the experience across the board. Then finally, looking at the observer versus player comparison, we found, as expected, differences in all conditions for all variables other than in GXR and PXR for physical presence and for interest and enjoyment. So intriguingly, what this means is that the XR mobile display helped bridge the experiential gap between players and observers. So this just goes to show how successful this very simple implementation was, because in these particular conditions, the observers had a similar experience, at least in terms of presence and interest and enjoyment, to the players who were actively in charge of the gameplay. So what are the take-home messages? First of all, simply providing agency on a static screen setup did not improve the observer's experience. It was really the physical agency through the XR mobile screen that can significantly increase user physical and social presence compared to the static screens. And finally, augmenting the player representation with real-life footage of the player did not have a significant effect on any of the dependent variables that were of interest to us. So essentially, in summary, the very simple and affordable XR mobile display was very successful at improving the experience of observers and acted as a window into the gameplay that brought the observer closer to the player and more in the middle of the action. Thank you very much for your attention. Please let me know if you have any questions, and don't hesitate to get in touch if you want to chat about this work or generally my work on embodiment personalized avatars too. Thank you.
Questions at all for Anca? Any questions? I had one question myself. Can you go back to your results slide? I may have missed something, but I just wanted to clarify. The one before that, I think. Oh no, the next one. Sorry. So in this one here, it seems like with the self presence, I'm just wondering if there's a significant difference across between the 3PC and the GXR conditions, or for the observer, not the player. So
for the observer, yeah.
So are these two different points here, are they significantly different as well, or is it just between the 1PP and the higher XR conditions? PXR
is also significantly higher than 3PC. Okay. So between these two. But and 1PP is also significantly lower than GXR and PXR. So there's no difference between 3PC and GXR. Okay, because I thought in the second one here, there's a clear step up when you get for the social presence and also the physical presence score, but with the self presence. And so I'm wondering, why do you think that is in that case? Yeah, it's a very interesting finding. So 3PC. I think it could potentially be because of the headset representation that was in PXR.
Okay.
So I feel like that's also, in a way, what we're trying to do here is to get rid of the barriers that VR kind of brings together with it. But because in PXR, the player still had the headset on, we couldn't remove it.
Yes.
That was still potentially a barrier.
This is an area for more research, maybe.
Yeah, absolutely. Yeah.
Does anybody else have any questions as well? And you'll be around during the day as well, and I guess you're also on the
Absolutely.
Discord channel as well. So
Yeah.
it's very interesting work, especially getting that qualification, or that you do have a benefit from having XR in terms of the presence and the gameplay as well. Great, let's thank our speaker again. Thank you so much. And our third talk is by Francisco. You've got your own HDMI port, don't you? You don't need this dongle. Okay, great, thank you. So once you plug that in.
Yes.
And so Francisco is from Politico Milano, have I pronounced that right? In Milan. Actually, now he's working in Germany, and you're presenting you're the second author. So you're presenting the paper with Giuliano as well, and so it's Francesco Vina who's going to present now. And he's going to be talking about exploring communication amongst people with neurodivergent or neurodevelopment disorders during cooperative play and augmented and virtual reality. So it'll be very interesting talking about neurodiversity. So I'll turn the time over to you. Thank you very much.
Thank you for the introduction. I think I can start, right? Okay. Hi, everyone. I'm Francesco, and today I want to present the result of this research on communication among people with NDD during cooperative play in augmented and virtual reality. Just for a little bit of introduction, what are neurodevelopmental disorders, what are NDDs? It's a group of conditions, it's like an umbrella term, conditions associated primarily with the functioning of the neurological systems and brain that very frequently affect social and communication skills and also other daily life skills. Common NDDs are usually autism spectrum disorder, ADHD, language disorders, motor disorders, and usually one issues with NDDs, it's then they could happen together. So there is also comorbidity between these conditions, and these reflect on social skills and communication skills in impairments in initiating and sustaining reciprocal interaction, and difficulties to use language and speech to engage in conversation with others effectively. So what we have done is social matchup. And social matchup is, in its first version, it's a VR cooperative game available for Google Cardboard, so with the Google Cardboard framework, let's say, who target individuals with NDD and try to enhance communication and cooperation skills. In 2020, we ran a study with 24 participants in a between subject study. So we had like 12 participants in a VR group and 12 participants that do the task in a physical, in a real setting. And the results were quite good for the VR condition because we noticed higher verbal engagement, more turn-taking, diverse utterances produced like declarative, interrogative, and lexical, and more time spent in the VR group, and when the speaking time was similar, in the VR group there were more silences, so the communication was more effective in the VR group. And the general user experience was positive for VR. This research was done in 2020, then life happened, and the Google Cardboard framework became a little bit outdated, and also AR proved to be effective for persons with NDD. So we went through some changes for social matchup. First of all, we changed a little bit the appearance of what the user could see. So we had very simplified content in the first version, and we tried this time to have like more complex 3D models. We had two different porting, one from the Google Cardboard framework to MetaQuest 2 and to HoloLens 2, so to standalone devices. And this reflecting also some interaction changes. So For the navigation point of view, we have before was static, the experience, so the user has to be sit. Now the user was free to move, and the gaze dwell interaction paradigm of the Google Cardboard was changed with the hand gestures. You can see the activity that we also ran in the first study was the sorting activities with balloon that the user are collocated in the same virtual environment or the real environment if, in case of the AR, they are back to back and they cannot see each other, what is on the table of the other, and they have to describe the balloon that they are taking and the position where they are putting the balloon. And this is like how the game resembles in AR and in VR in the second version of Social Matchup. And we ran a study. The goal was to investigate the effectiveness of both the new application in improving the conversational skills and to check if also this application were usable as the first version. Of course, participants were paired because the game is collaborative, so they have to play in pairs. And we chose the same task as the first experiment, but we changed the design of the study. It was a between subject before, and now we went for the within because we want the participants try both the technologies. Of course, the order of conditions were randomized. We also registered everything in order to do then linguistic analysis on the recordings, and we have questionnaires at the end of each experience. We recruited 30 adults on a voluntary basis from a therapeutical center in Milano. Average age was 32.8, 12 females, 18 males, and the diagnoses were like different. There was ASD, intellectual disability, motor disorders, and language disorders. We had few inclusion criteria. The more relevant was that, of course, the diagnoses have to be like NDD, but we discarded the severe NDD diagnosis for this case, and we also look for people that aim to be collaborative, at least. For the research variables, we kept the same linguistic metrics of the first study. So we had like the length of conversation divided in silences and speaking time. We have different utterances. Here we diversify in single lexical word, interrogative clauses, and declarative clauses. We count the number of turn-taking, we count the number of word per session, and then we add questionnaire on top. This was a limitation of the first study because questionnaire were not so, let's say, taken from literature. And this time we used the SUS, the CIQ, and the UAQ score. So, regarding usability, we got 2 very good usability scores for the AR and VR applications with, and then we ran a parity test between the 2 scores, and Smooth VR were significantly more usable than the AR application. For the CIQ, it stands for Customized Interaction Questionnaire. It's a questionnaire for interaction in virtual reality and augmented reality. It has like 20-ish items divided in 5 categories. We only found a significant result for Smooth VR in quality of sensory enhancement categories. All the other categories were not significant. We ran then item per item parity test. We found some significant that you can find in the paper. For the UAQ, instead, the results were also good in this case. No significant result for hedonic, pragmatic, and overall quality, but item by item, we noticed that the second item and the fourth item were significant for the VR application. So the second item, it's related to the easy to use, while the fourth item to the clarity of the application. Concerning the linguistic metrics for the conversation length, in AR there were significant longer speaking times, while for Smooth VR, user completed task faster, so also this was significant. total word produced, there were like more words produced in SMOOP AR compared to SMOOP VR. For utterances also, we have that SMOOP AR was like produce more declarative clauses and more single lexical words than SMOOP VR. Concerning turn taking instead, we don't have nothing that was like different, no big differences. So coming to discussion, both the application show to be usable. SMOOP VR was more usable than the AR application. But the AR application had higher speaking time and completion time. But this, we saw that was also due to the difficulties that the individuals encountered during the application. So even if the application was usable in the AR application, there were like more challenges. These challenges were particularly interaction challenges. And they were like, since they were using the HoloLens and also in the MetaQuest 2, they were using the hand tracking, some gestures were not so intuitive to do. Concerning the sensory enhancement, instead, the SMOOP VR proved to be more effective, but I mean, this is also like, we expect this because since VR, it's more immersive. Concerning the communication part, we had an higher word production in SMOOP AR. The speaking time was also significantly higher, but the VR had lower speaking time. So it means that the VR application was more effective in delivering communication between individuals. The SMOOP AR produced more declarative clauses and single lexical words. For declarative clauses, we mean something like, I have placed the red balloon, so what the user was doing in that moment, while single lexical words were like interaction of one word, like done, okay. And since the AR part had more difficulties in doing this, we also expect a more production of words. So for concluding, the objective of this study was to assess the impact of AR and VR on communication and cooperation skills in individuals with NDD using these new developed versions of social matchup. The study results show that both the applications were usable, the VR more usable than the AR, and the AR show in the end more verbal production, which is still good since we want to tackle that aspect. Challenges were mainly for AR, for the end position perception, for VR, in the fear of moving without knowing where to go, because in the previous experience, the user was sit, in this case instead was free to move, and not be able to see the real world was triggering the user sometimes. For both versions, gestures were a challenge, and this is also like a result that I found in some previous research with AR and people with NDD. For behavioral insight, communication sometimes required initial intervention, but improved over time, and participants frequently discussed the game post-session, even those less communicative during the gameplay. So also after there was like an impact on communication. Thank you for your attention, and I'm here to answer questions.
Thank you. That was very interesting. Does anybody have any questions in the room for Francesco? And Katja, is there any questions on the Zoom link as well? Could you, not yet, maybe. Any questions? Oh, there's one at the back there. Do you need a microphone, or are you going to use your outside voice? Okay, project. There we go. Oh, she's got a microphone. There we go.
Thank you. Thank you very much for the talk. You mentioned that part of your screening process was to kind of like discard the people that had an NDD that was severe, right? Kind of like, I guess there's multiple questions here, right? Kind of like, how did you decide what that threshold was, first of all? And then your results then are with that set of population that you would say that has a less severe NDD, right? So how would this generalize to a population with a more like severe aspect? And how does that inform the design of AR and VR systems for this population?
Thank you for the question. I will make an example of a severe case. A non-verbal individual could not do social matchup at all, because if you're non-verbal, I mean, it will be also useless to try. This was like more or less the reason why we discarded the severe diagnosis of NDD. Of course, we didn't do it ourselves. We asked the center to provide us individuals that were like able to run a study without incurring in any problems and any issues, because we want like safety first and then run the study in safety, I would say. But yeah, we ask experts this, and also sometime in daily care centers, the kind of diagnosis that people have, it's not so strict, and they also do a kind of self-assessment. So sometimes you also receive diagnoses that are not so precise, but they are only a degree of severity. And so we could like discard the real severe diagnosis in this case.
Did you have a follow-up question? Oh, she's got a question down there. We can bring the microphone over in a second. Okay.
Thank you for your talk, really interesting. I had a question about the result that you got with the AR version, that they had to discuss more. And I was wondering, was there also visible frustration in having to communicate more? And what is your opinion on using this, if it's not an impediment, to use actually this longer talking these longer talk that are necessary as a therapeutic tool, right? To kind of accommodate to and help them talk more, for example, for ASD diagnosis, right?
Thank you. In AR, there were like problems that were related to the interaction, but also sometimes due to lights, because we use the HoloLens, and the HoloLens, since you have holograms, so there were like also problem with light sometimes, and I mean, we took everything in the end for good because they were talking, and usually they don't. So I mean, it was a way also of communicating, also if you complain about everything. And this was good also when we saw that they were discussing the game mechanic also after the session. So I mean, if I understood well, the question is, I mean, was good that they do this? I would say yes, because in the end, I mean, we also the therapist noticed after. I mean, we leave this application also to the center, so they did practice. We did at least once a week, and they saw that they were like happy to use the application, and while they were using, they were communicating. So the effect was there. We didn't measure like the improving after time. This would be like a follow-up, probably. Thanks to you.
So let's thank the speaker again, and he'll be here the rest of the day as well, so you can talk to him some more after the session if you like. So please thank him. Great, thank you.
Thank you. Yes.
And the last presentation is online. It's from Hye-Young Kim and Singmin Choi from Posttech in Korea. So, and I don't believe that either of them are on line right now. So I think we'll just watch the video, and if we have questions, we can then email them or ask them as well. So can you please play the video for us? That'll be great.
The social intent of touch initiator in virtual reality using multimodal haptics. Social touch refers to using touch with social intents between co-located individuals, and its effects have been found across various domains. First, touch is a powerful and intuitive way to convey emotions. It also plays a key role in building close interpersonal relationships. Additionally, it can influence the attitudes and the behaviors of others. However, it is difficult to expect such social touch interactions in virtual environments. While VR offers immersive audiovisual experiences for interacting with virtual characters, it still lacks enough tactile elements. Various methods have been proposed to emulate human touch through haptic technology. Studies show that technology-mediated touch can convey the social cues inherent in human touch. However, there are still some limitations. Most approaches rely on single modality haptic feedback, usually vibrations. This restricts the range of tactile sensations and simplifies the touch experience. For literal interactions, we need multimodal haptic feedback. Another issue is that a lot of research focuses on the recipient's experience of passive touch. But since touch is a two-way process, it's also important to consider the haptic feedback for the person initiating the touch. To address these limitations, our research focuses on the touch initiator who actively engages in touch and explores how multimodal haptic feedback can improve social interactions. The goal of our paper is to explore the design and effectiveness of multimodal haptic feedback in conveying the social intent of a touch initiator in VR. To achieve this, we conducted 2 user studies. In the first user study, we explored the haptic characteristics crucial for representing touch gestures depending on social intent. In the second study, we looked at how multimodal haptic feedback impacts the virtual social experience for touch initiators. Let me explain the general method we used in our user experience. In the virtual room, users were represented as first-person avatars with synchronized upper body and hand movements, facing a virtual agent seated across from them. To detect touch, the colliders were attached to the user avatar's fingertips and the virtual agent's forearm. The touch area was limited to the forearm, which is generally regarded as a public and easily accessible body area. When a touch was detected, multimodal haptic feedback was presented to the corresponding finger. We used the commercial haptic glove to simultaneously provide cutaneous force, thermal, and texture representing vibration stimuli. In our user studies, we selected and used the 6 social intents: happiness, sadness, fear, and anger to convey specific emotional intents, calming and gratitude to convey prosocial intents. We prepared the scenarios for each intent. Now let me share the details of the first user study. To investigate the key haptic characteristics for expressing touch gestures based on social intent, we designed 2 tasks. First, participants were presented with 6 social scenarios and asked to respond with all the touch gestures they might use in each situation. Then participants entered the VR environment and performed the touch gestures they had previously responded. While experiencing haptic feedback, they selected the most suitable haptic parameters for conveying the intended tactile messages. Participants were provided with 4 distinct stimulus options for each of the 3 haptic modalities. This included unknown option, which deactivated the stimulus, and 3 different stimuli. We had 24 participants in this experiment. The touch gesture survey results showed significant differences in gesture preference across all scenarios. The most preferred gestures were used in the next steps of the study. As per the key haptic parameters, a common tendency exists among users to haptically represent touch gestures based on social intent. Significant trends were found in stiffness and temperature. For stiffness, participants tended to respond based on the pressure they expected to feel from the touch gestures and the arousal level of the given scenarios. In intense emotional scenarios like anger and fear, participants preferred higher stiffness, while in prosocial situations such as providing comfort or expressing gratitude, they favored low to moderate stiffness. In the case of temperature, participants tended to respond based on their subjective views and experiences, linking them metaphorically to emotions. Generally, it was associated with anger and excitement, warm temperatures with positive emotions, and cold temperatures with negative emotions. Now let's move on to our second user study. The goal was to assess the effectiveness of multimodal haptic feedback on the virtual social experiences of touch initiators, also including a passive haptic proxy. We compared 4 haptic conditions, and I will explain each one. First known condition was the control condition, where participants experienced touch visually without any haptic feedback. Passive condition provided the virtual agent's physical proxy as a tangible interface, enabling nature tactile exploration. In the active condition, participants touched the virtual agent's arm using a haptic glove. First, thermal and vibration stimuli were delivered to the fingers based on parameters selected from the first user study. The augmented condition combined passive and active feedback. While touching the physical proxy, its tactile responses were modulated by the multimodal active haptic stimuli, conveying the social intent of the touch initiator. This experiment consisted of 4 sessions with different haptic feedback conditions in a within-subject design. Participants experienced haptic feedback as the touch initiator using the assigned gesture for the 6 scenarios, and then completed both the post-trial and post-session questionnaires. The post-trial questionnaires consist of 3 questions assessing the adequacy of the haptic feedback in expressing social intent, as well as valence and arousal to evaluate participants' emotional responses when touching the agent. The post-session questionnaire designed to measure the overall social experience after each feedback condition, including co-presence, avatar embodiment, and emotional closeness. We had 20 volunteers for this study. For low arousal scenario, passive condition was the most effective, especially for expressing calming. Participants mentioned that this condition provided a soft tactile experience not found in the other conditions, fostering a deeper interaction with the partner. The active condition received lower scores across nearly all scenarios than conditions with a physical proxy. This indicates that providing a solid surface is a crucial element for enhancing social touch interactions. Some participants expressed disappointment that their hands passed through the virtual agent, which made the experience feel less realistic. The augmented condition constantly scored high across all scenarios and was particularly effective in intense, high arousal situations like anger and fear. In addition, the augmented condition was found to make the valence of anger and fear more negative while increasing arousal, thereby amplifying these emotions. Participants say that the controlled force and temperature feedback enhanced their emotional immersion and made the experience feel more vivid. For co-presence and avatar embodiment, the passive condition was the most effective. Passive haptic feedback therefore offers significant benefits in making virtual touch interactions realistic and natural. The augmented condition also received similarly high ratings. Notably, it was the most effective in enhancing emotional closeness with the agent, suggesting that social intent-dependent feedback effectively reduces emotional distance with the virtual agent. In conclusion, multimodal haptic feedback enhances the virtual touch experience, particularly when aligned with social intent. Specifically, modulating haptic properties based on intended message heightens the social expression of virtual touch. Combining active haptic feedback with tangible elements show the most significant results, greatly enhancing the virtual social experience for touch initiators. Thank you so much for listening to this presentation.
So as far as I can tell, she's not online right now, so we can't ask any questions, but you can certainly follow up with emails, things like that. So that's it for this session. Please head outside and you'll join the lines for lunch, and then we'll be back at 2:30 for the afternoon sessions as well. So thank you very much for your time.